Welcome to the advanced tutorial session for Lab 24, the Performance and Tuning Lab. My name is Joey Dickhans. I'm a performance specialist in the technical marketing organization at VMware, and I'm joined by Paul Mannington.
My name is Paul Mannington. I'm a senior technical trainer in Europe, training the internal technical audience.
Yeah, so if you hadn't seen, there was a little email sent out earlier to some of the VMware guys and to the guys that are attending VMworld. And Lab 24 is the third most popular lab right now. Woohoo! So we're only being outdone by the new View 4.5 install and configure, which is a pretty basic one. I know why everyone would jump into that one. And the what's new in 4.1 features, so I can understand why that one beat us too. But anyway, still excited about that. Alrighty, so let's go into this. If you haven't seen the lab environment downstairs, it's really pretty nifty what we're doing this year. It's all in the cloud, and each lab is designed as just a collection of virtual machines. And we've packaged up these virtual machines into what we call a vPod, just a name for the collection there. And when you sit down at one of the stations, they log you in. You get to select from a list of 30-something labs. And each one of those labs is created as this vPod. And when you select 24, because that's the one you're most interested in, it goes and it takes that collection, it dumps it out onto a server, deploys it onto a server, and away you go. It would be great if that was the picture, because then we could do a nice performance lab, we'll get consistent results, it would be wonderful. That's not exactly the picture. The picture is something like this. We've got 200 servers down there, but we've got 480 concurrent labs potentially going on at one time. It is pretty packed down there, and the line's out the door. So that could cause a few problems with the performance lab. So your results may vary, and they actually may vary in this demo as well, because we are connecting to the same environment that's downstairs. So everything that you see downstairs is occurring to us up here as well. All right, the performance lab is broken into three sections. We've got a storage performance section where we talk about detecting storage congestion, explaining what disk shares do and what they don't do, explaining the new feature in 4.1 called Storage I/O Control, which is a new way of managing your storage workloads. We'll then go into memory performance and memory overcommitment, and we'll talk a little bit about that, and we'll talk about the impacts of swapping when you do have memory pressures and you have to swap out to disk. We'll talk about how big of a performance impact that is. And then we'll also talk about memory compression, which is another new feature in 4.1, and how memory compression can help you a little bit when you do have memory pressure. Instead of swapping out to disk, we now can have this new technology that will delay how much we have to swap out to disk. And then lastly, Paul will go into our CPU performance section, and we'll detect CPU saturation in your environment. We'll talk about the appropriate and inappropriate uses of SMP, multiple vCPUs in a single VM. And then we'll talk about how we could correct this with resource pools or DRS. All right, so jumping into the storage part, and we'll be flipping back and forth between the slide deck and the actual hands-on lab that you would be able to do downstairs. We were trying to have two screens, but we only got the one, so we'll have to be switching back and forth. So, all right, so the storage performance portion of the lab, it's a very simple setup. We've got one EXX server. Now, these EXX servers are, again, in the cloud, so there's actually a virtual machine running EXX, and that virtual machine is running on top of EXX. So there's a couple of layers of indirection here, but pretty much it looks like an EXX server to everybody. And then on top of that EXX server, we've got two virtual machines. We've got VM1, which is our high-priority virtual machine. And it's running just a simple storage tester, a little performance tester tool, and we'll see it in a bit when we log into the lab. VM2 is our IO-Hog workload. Now, our IO-Hog workload is going to generate a lot of traffic towards the data store, and it's going to really start saturating the storage array, and we'll see that it's going to cause some performance with VM1. Now, if we did this using the shared storage infrastructure of the lab, they'd probably string me up and kill me because we're already having some pretty interesting storage performance on our storage array in the lab. So instead of going directly to the storage device when we launch this IO-Hog workload, VM1 and VM2 are using a RAM disk because we do have enough memory in the servers. So it's using a RAM disk that's simulating a single disk spindle. All right, so we have to trick some things out in the cloud environment just so we don't really mess everything up for everybody. All right, so VM2 is running that IO-Hog workload. We just grabbed Iometer or Iometer, however you want to pronounce that one. It's a really cool tool if you haven't seen it before. This is a storage load generator tool. And it's also a performance measurement tool, and it's a good way of baselining your storage if you haven't used it before. It can create a lot of interesting metrics, number of IOPS that you're able to push through your storage, throughput in megabytes per second, average latency that you're getting from the storage device, and we'll talk about how important that can be, and just CPU utilization inside your VM while that's going on. All right, so that'll be the tool that we'll be using inside the VM2 I/O workload. All right, we're going to switch over to the lab, and we're going to have Paul sort of do the hands-on portion here. All right, so we're just going to power on both VMs. And it may take a while, so I don't have any good jokes anymore, but I won't even attempt. Iometer is free, yeah, just available, just, web search it. Yes? It's pretty accurate, so there's always this question about how accurate are the in-guest performance measurements. And when you're not running out of CPU on the physical server, the in-guest performance metrics are relatively accurate enough for government work. All right, so we're starting up the two VMs. We've opened the console to VM1, which is the high priority VM, the one that we're interested in. It's automatically going to log into the Windows desktop, and it's going to start running the performance tester tool. And we'll see that little performance tester tool, hopefully in a second here. All right, how many have actually already done a lab downstairs? Brave the line. Wow. All righty, excellent. Well, we're actually doing a little contest here to see how many people can, who does the most labs, and then there's a little raffle at the end. We've got one gentleman down there who's already done 24 of the labs out of 30, so I think he's just been spending his nights there or something. Alrighty, so here's the little performance tester guy. He's already pretty unhappy. He might get a little happier as the storage array, as well, the RAM disk and EXX itself starts caching a few things at the EXX hypervisor layer. But in general, he's going to remain around this unhappy level. And so we're going to quickly go over to the Performance tab for VM1. So we've selected VM1. We go over to the Performance tab for it. And we're going to look at just the first screen you see in the Performance tab is this overview screen. And this overview screen has multiple charts in it. And we also have to scroll because of the resolution here. But it's got things like CPU utilization, memory utilization, disk latency, your memory throughput, that type of thing. It's a really nice dashboard to see what's going on in your VM. So if you've got vCenter installed, go in there, look at it. This is probably the first place you want to look just to see a graphical representation of what might be going on in your VM and might pinpoint some things that you want to drill into. We sort of already know that this is a storage performance problem, so we're going to go to the Advanced tab of the performance thing, the Advanced button, and we're going to go drilling down into the storage performance metrics. All right, so just select the data store there. We're interested in the data store measurements, and we're interested in real-time measurements. And we're going to select both data stores, and then the things we're interested in the most are read and write latencies in this example. Now, storage and storage performance problems are pretty much the number one performance issue that our virtualization customers get into. So this is probably, if you don't exactly know where to start, storage is probably your first spot. All right, now we just started the workload. So the chart up at the top is the history of what this VM has been doing over the last hour or so. But we just started it up, so the history is pretty much blank. Except if we scroll all the way over to the right, we can see that little lines have started to appear plotting our performance metrics that we're interested in. And if you hover over those lines, you can get the measurement at that point in time, so you can go back and forth in the little chart. But more interesting for us is, because we just started this thing up, it's just going down to the legend at the bottom. And you can see the legend with the two data stores that we've selected. And you can also see that the latest measurement there, that is the new sample that's coming in. And so vCenter polls every 20 seconds, it collects it, and it throws it into the chart. But we can just see it right here in our latest measurement. Now, one thing you'll notice is that the primary storage, this is the storage that the operating system for the VMs are using. It's the shared storage amongst all the VMs and all the labs downstairs. It's doing okay. We're not issuing that many IOs to it anyway, but those IOs that we are issuing to it are completing relatively fast, 3 milliseconds or so. The storage, this SIOC data store one, this is the data store that the application, the performance tester tool, and Iometer are both banging away at. And you'll notice that its performance is kind of high. It's got 37 millisecond latencies on the writes right now, 30 on the reads. It's a little high. Generally, we like to see latencies below 30 milliseconds. Now, this is a general guideline, and so with all performance talks, again, your results may vary. Depends on your workloads, depends on your SLAs, how much of a storage performance hit you can handle or not handle. All right? But in general, 30 milliseconds or above is probably an indicator that you're having a storage performance problem. All righty. Let's switch back to the slide deck here. I'll just quickly go through some of the things we saw. We saw the performance tab. We saw going into the advanced chart settings here. And in my example here, I have a lot more history because I let it run for a lot longer before I took the snapshot. But again, we looked at the legend. We saw that latencies were around 30 milliseconds or maybe a little bit more. So what's going on? And we'll do this in slideware here. We've powered on VM1. VM1 is the small little performance tester. It issues a few IOs into the device queue inside the EXX server. And those IOs then trickle down into the storage array. And it uses up a few storage array queue slots. And because the storage array now has to process a few of those IO requests, the average latency for each of those IO requests gets a little bit high. Well, right now it's kind of small, but higher than 0. It's 2 milliseconds, hypothetically, in this slideware example. We power on VM2. VM2 is our hog. It starts issuing tons of requests into the device queue. And so it issues quite a few of them. Those propagate down into the storage array queue. And the storage array queue now has to service those requests along with the requests of VM1. And because of that, it starts introducing a higher latency. This is a higher average latency. So this is the average latency across all the IOs that the storage array is handling, including VM1's. So VM1's average IOP latency was 2 milliseconds before. Now it's 30. And we have congestion. So under congestion, again, hypothetically here, we've jumped up to 30 milliseconds and our throughput goes down. We get unhappy. And in the past, we used to control storage workloads using disk shares. We went in, we told you go in there and assign your high priority storage workloads high shares, assign your low priority ones low shares. In this particular, they worked okay in some examples in some areas. But in this particular case, could we use disk shares to control this? And the answer is no. Disk shares control access control into this queue up here. Okay? So when this queue up here gets congested, that's when it says, I have no more slots. All right, you have priority. I'll let you have a slot. Okay, you've got this number of disk shares, and that means you have this many slots. And it sort of does this little access control algorithm. In this example, we don't have any congestion at this level. Notice we have a few extra slots up at the top. So if IO2 wanted to issue VM2 wanted to issue a couple more IOPS, it could. There's no problems there. If VM1 wanted to issue a couple more IOPS, it could too. There is no congestion at this level. Disk shares aren't going to help prioritize between VM1 and VM2. So what can we do? Well, we've got a new storage control mechanism called storage IO control, new in 4.1. And it monitors the storage latency that's occurring down at the storage array level, and it's able to manage that. And the way it manages that is it uses this congestion threshold. And we tell it, all right, we would like to see average latencies of around, and by default it's 30 milliseconds. All right? And what it'll do is it'll say, okay, well, if we're above 30 milliseconds, I will try to get down to 30. So in our example in the lab, we've actually set it all the way down to 10 milliseconds, which is the lowest you can set the value to. We've done that not because we think it's a best practice or anything. I'm not saying that it's a best practice. We've actually done it only because we want to make the little storage performance guy change in a more noticeable way and more reliable way. So that's why we set it down to its lowest value. But what it'll do when we set it down to 10 is it'll start controlling this. It'll start dropping the number of device queues you've got at each EXX server that's using the data store that we're controlling. And it'll drop them down such that there is congestion now at that device queue. Disk shares will then start working and prioritizing the VMs if it has to because of the new congestion that we introduce up here. All right, so let's see this in slideware. Let's turn it on. We'll see it in slideware, then we'll have Paul do it in the real lab here. By default, it's 30. In the lab, we set it to 10. And when we first turn it on, storage IO control will detect that we're above the congestion threshold down here, and it'll start trying to work. And so it'll drop it. Originally, it was at 30, 32, and we drop it down to 26. Nothing happens. Nothing changed, right? Those were free slots not being used anyway. Then it drops it down a little bit more, drops it down to 20. That reduces how many IOs that VM2 is able to get down into the storage array. Because it's not being able to get into the device queue, that means it's not being able to get down into the storage array queue. Now you might wonder, what happened to those that we just prevented from getting into this queue? Well, there's actually another queue on top of this one inside the EXX server called the EXX kernel queue. And now the kernel queue, when normally running, doesn't have anything in it. And your IOs don't spend any time in it, because normally you can get a slot in your device queue right away. So we generally like to see latencies less than 30 milliseconds. We don't want to like see things in the device queue for more than 30 milliseconds. In the kernel queue, we really don't like seeing anything in there at all, ever. That sort of means something's going on. But if you see anything under 2 milliseconds is okay. Anything above that might be a performance concern that you would want to investigate. All right, so now storage I/O control still hasn't met its congestion threshold, so it's going to continue to do this until it gets down to its storage congestion threshold. All right, now because these things have equal shares right now, you'll see that it actually has a little bit more. VM2 has a little bit more, and that's because we haven't gotten to a point where we started to have to control VM1. VM1 is able to issue as many IOs as it wants as it's requesting, and we haven't actually impacted VM1 at all yet. All right, let's switch back to the lab and see this in real life. Yeah, if we want to just scroll back to see that, I'm hoping that he's still unhappy. All right, he's still unhappy. We proved that he's still unhappy. All right, we're going to go into the EXX server, and at the data store level, if you right-click on this and say Properties, you'll see that now, to enable storage I/O control, it is one checkbox. That is it. We had so many complaints saying disk shares is a per VM thing. We got to log in and assign them. It's a pain in our ass. So we can now set this at a data store level. Every EXX server that is connected to this data store automatically has it set. It's a data store property. Anything that uses it has it set now. You have a question?
Licenses? Which licenses?
The licenses, I believe this is available in the base product, but don't quote me on that one. But I think it is available in the base product. All right, so here's the advanced setting where we can set the congestion threshold. By default, it's 30 milliseconds. That's a pretty conservative value. The idea here is we don't want storage I/O control to be triggering. Go ahead and say OK. We don't want storage I/O control to be triggering all the time, because that means we're throttling back workloads. So if it's always running, then you probably have a storage array problem. You probably have sized the storage array too small, or your workloads are just running wild, or something else is running. Storage I/O control is designed to protect you for that peak period of time, that spike that occurs during the day, and you want to have better control over which VMs get the priority.
Is there any type of server you would say, or workload you would say you wouldn't want to turn this on?
I don't know if there's a workload that you necessarily wouldn't want to turn this on. Again, you wouldn't want to turn it on you wouldn't want it running all the time. So we just clicked enabled, and if we weren't hitting that congestion threshold, storage I/O control would only be monitoring to see if you are above it. It wouldn't be throttling workloads. We wouldn't want to see it kicked in and doing something of throttling your workloads all the time. But I don't think there's any particular workload that you would say this would be a problem to you. Yeah. All right, so you notice that our performance jumped up. Here he is. He used to be red. Now he's a little happier. We've been able to give him more storage performance because we've hit this storage I/O control. All righty, we're going to switch back to the slide deck just a... Oh, yeah, I think so. Okay. Question?
Is this conflict with storage DRS?
Where is storage DRS?
Coming down the pipe.
Okay, all righty. So now this is probably the foundation for storage DRS. All right, monitoring what the latencies are on the data store and seeing if we can control it locally, and then potentially moving it over. So storage DRS isn't quite out yet, as you know, and this is not storage DRS. It's not going to start storage vMotioning things off to data stores. Yes?
Can you enable storage I/O through Power CLI?
I believe you can, but I'm not the Power CLI guy. I think it is just a property on the data store, and I think you can do it through the CLI if you needed to. Yes? No. So it works with any storage arrays. It only works with Fibre Channel and iSCSI right now, so not the NFS. But there's nothing firmware-wise that you need on the storage devices. All right, one last question here. And yeah.
I was going to say storage I/O does require Enterprise Plus.
Oh, okay, excellent. Thanks for the licensing update. So it is an Enterprise Plus feature then. Alrighty. One other thing, how do you observe what storage I/O control is doing? So we've got a common question, can we get any alert when it actually starts kicking in and starts throttling things? We don't get an alert that it starts throttling things. It is something we've suggested to the product management team to introduce. But you can go in and see if it's doing something. And it's provided two new metrics inside vCenter, storage I/O control normalized latency and storage I/O control aggregate IOPS. We used a normalized latency here because you can get different latencies on your IOs if the IO size is larger, if you're issuing more IOs. So we want it to be fair when we started balancing workloads between VMs. If one VM is issuing larger IOs, maybe we need to balance that from a VM that's issuing smaller IOs. So we've normalized it, and there's a function that we use to do it, but it's normalized for size and for the number of IOs that each VM is working. All right, and that normalized latency is what storage I/O control uses against the congestion threshold. So if you've got a particular workload, it might not be seeing the same actual device latency that storage I/O control is calculating is its normalized latency. But you can see this if you go to the data store screen and you go to properties, you can see both of these metrics, the storage I/O control, normalized latency, and the aggregate IOPS. And you can see we're dropping the storage I/O control congestion value in this screen, and the latency was going down as we kept dropping it. All right, one other thing that you can interestingly see on this same screen is your max queue depths. So the way storage I/O control works is it adjusts the max queue depth, so you have less slots that forces disk shares to work. If you go to the data store screen and go to the performance tab, you can see the max queue depths, and you can see what storage I/O control is doing to adjust the max queue depths. And in this case, you can see that we had to keep dropping the queue depths down as we reduced the congestion threshold. Alrighty. One more thing, interesting. Storage I/O control, when it's enabled, has a capability to detect external workloads that are generating latencies on your storage arrays. So we've got a lot of customers that are sharing their SAN storage, right? You've got this gigantic storage array, and you're using some of it for your virtualization environment, and maybe you're still using some of it for a physical server that's running your database or something, whatever. We'd love for you to move that over into your virtual environment too, but you still have that one physical server running its database, whatever. And all of a sudden, the database starts kicking up. It starts generating a lot of I/O to your storage device, and your storage device starts getting that extra latency. Basically, the I/O hog that we had in VM1 is now the I/O hog of a physical server. That physical server is not being able to be controlled by storage I/O control. It can't throttle that workload because it's not under storage I/O control's privy. It can't do it. So what can we do instead? Well, we can detect it. So storage I/O control will detect that, oh my goodness, there seems to be a large latency on the storage array coming from somebody external. It's causing me to go above my congestion threshold, and there's nothing I can do about it. It'll trigger this alert for you. This is kind of a nice little alert. I know that alerts look bad and scary, but this is kind of a nice one for you, because if you are a VI admin, you now have a little bit of evidence that might not be you. It might not be your environment. This might be a storage admin's problem or maybe some other person's concern. However, there are a couple of cases where it still might just be you. It could just be the storage array. The storage array could be doing something. Maybe a disk has failed in the storage array and it's doing array recreation. So it could still be some other things that are generating a latency outside of storage I/O control's control. All right. One new feature, and we'll show it here, and then we'll go into the thing. Actually, we'll start it up. Is I/O limits. So not related to storage I/O control. This is available, but for a long time, we've had the ability to set limits on how much CPU you've been able to use, how much memory you've been able to use, but we haven't had a limit on how much disk you can use, how much disk resources you can use. And now we do. So now we have a limit that you can set a maximum number of IOPS that a particular VM can issue to a particular data store. Now, it is per VM per data store. So if you have multiple virtual disks on the same VM, on the same data store, you have to assign the limit on both of them. All right, because it's going to go and it's going to add up both limits, and that's how many that VM can issue to the data store. So if one has unlimited and one has 250, it'll add them up and it'll say you have an unlimited plus 250. Both of them can issue unlimited, all right, on the data store. But anyway, we only have one disk per data store. The top disk, again, is our OS disk. Its data store is the primary data store for the rest of the shared environment. And this disk here is our disk on the other data store that VM1 and VM2 are sharing. All right, so Paul's going to go in here, and we're going to set an IOP limit. We sort of know, because we've been running this a lot, that the IO hog workload is generating about 1,600 IOPS. So we're going to set it to half that. And you'll see that right away, we set the IO hog until I can only use half. Whoop, performance goes straight through the roof. Alrighty. We're going to clean up the lab there. So that's the end of the part 1 of the lab. We'll just go into some storage best practices. Yep, one question. So you don't need anything special inside the virtual machine. So storage I/O control is at the EXX host level. It's transparent to the virtual machine. So no VM tools necessary or anything like that. All right, so storage best practices here. We get this a lot for some reason. We get people who are going from a physical environment and they're consolidating down to a virtual environment. They say, you know what, we've got 10 physical servers. Each physical server has 2 disk spindles out in our shared SAN array. We're going to consolidate that down into 2 physical servers, each having 5 virtual machines on it. So I guess that means because we only had 2 spindles per physical server before, I guess that means we only need 4 physical spindles now? No. No, you need as many spindles as you had before if you're going to be running that many VMs in your virtualized environment. And in fact, you might need a few extra because typically when you're in the physical environment, your operating system is generally on a local disk in that server. And in a virtual environment, your operating system is on the data store someplace out in your shared environment. So you might need a few extra spindles to handle for that. So do size your storage arrays appropriately. 30 milliseconds is our guidance. For anything above that is a potential storage problem. We talked about the kernel latency. So 2 milliseconds or more is potentially a performance concern. Now, when storage I/O control kicks in, the low priority workloads, they're still issuing IOPS, all right? But they're not getting into the device queue because storage I/O control is preventing them from doing that. They're actually ending up in the kernel queue. And they will be spending a lot of time in the kernel queue before it's able to get a slot in the device queue. All right, so when storage I/O control is enabled, you might see kernel latency jump up a bit. And that's probably because your low priority VMs are spending some time in there. And that's probably what you want. So if storage I/O control is kicked in, kernel latency might go up. All right, we talked about storage DRS. This is not storage. Yeah, real quick. You can use it for local storage, but it makes a little bit more sense when it's in a shared environment. But it works just fine with local storage as well if you wanted to prioritize that way. Yes, one last. What? I'm not too sure whether it's able to work with the raw disk mappings yet. I have to work on it. So it's not DRS, it's not storage DRS. So if you are noticing a large imbalance between your data stores, you notice one is getting a large latency, one's not, you might want to go in there and manually use storage vMotion, manually balance them out. You can use storage I/O control again. It's to protect your peak periods of time and to prioritize your workloads during those peak storage spikes. And then there is a new feature. We talked about how storage I/O control doesn't require anything new in the storage arrays. But we do have a new feature in vSphere 4.1 and as well in the new storage arrays coming out from our vendors is VAAI, which is the vStorage APIs for array integration. I think I get that right. I hope I got that one right. But anyway, that allows you to do some of the management features of like storage vMotions between 2 LUNs on the same storage array. You can storage vMotion those a lot quicker. It offloads the workload of moving things around and copying things to the storage device so it can do it itself locally. All right. One last thing that I wanted to mention. When the storage performance guys heard that we were giving this talk, they said, we really want to get feedback to the customer feedback on what type of tools they would like to see in a storage performance testing tool. And Iometer is a pretty good one. This is a simple little testing tool that they created, and you can play with it in the lab if you wanted to. It's very, very simple. But the whole point of it is to get your brain juices going and to start providing some feedback for them on what things you'd like to see, what type of storage workloads you want to be run in a tool. Is it Iometer? Is it like Swing Bench? Is it some other workload? What type of workloads you want to see, what type of metrics you'd want to get back from EXX or from the guest, and how would you want the results displayed. Just simple things. And if you have any suggestions or comments, there's the email that gets directly to our storage performance guys. So it might be interesting to talk to them. And you can also fill out comments on the survey, which is something that we didn't mention in the beginning. There is a survey at the end of this, and they do ask us that you do fill it out if you could. All right, we're going to jump into the memory portion of the lab. And we'll see what our time is. So on the memory portion, we've got, again, a very simple environment with one EXX server, one VM. We've assigned the VM 800 megabytes worth of memory. And then to induce a sort of memory pressure situation, we've assigned a limit of 512 megabytes. All right? And this little guy, this VM7, is going to be running the same exact performance testing tool. At least it looks the same exact tool, but in the background, we're able to change whether it's doing a storage test or a memory test or a CPU test. So before it was doing a storage test, now it's going to be doing a memory test. So even though it looks the same, it's not still doing the same exact test that it was doing before. All right, we're going to switch over to the lab. And we'll see that, okay, we've started up VM7 already, so you didn't have to see it power on. The little tester guy is running. If we were good, he'd be running happy in the green zone. The green zone is 600. He's right now at 575. We just, for some reason, things are just a bit slower right now. So he's not running exactly green, but he should be. And now we're going to go ahead and set the limit. Now, by default, memory compression, which is the feature that we're going to try to showcase here, memory compression is on in 4.1. It's one of these features that you probably don't ever need to turn off. It probably will always provide you benefits if you do run into a memory overcommitment and memory pressure. But just so we can show you bad performance first, we're going to we've turned memory compression off. So this little example is running with memory compression off. We've also disabled a couple of other things. You probably know that we have transparent page sharing and things like that. We've disabled that just so we can highlight the difference between swapping out the disk and using memory compression. All right, so have you set the limit? Okay. Okay, so you've set the limit. Now, we've been noticing this downstairs. It is starting to swap out to disk. It is hung. So we've noticed this, and we've told people, wait a minute or so. In the lab manual, it said wait a minute or so, and it should go red. And people have been very, very patient downstairs, and they have waited 5 or 6 minutes waiting for him to turn red. We will give him a little bit of time, but if he doesn't change, we're just going to move on. He's hung. You'll notice that he's not updating his little number there. All right. Now we're going to go back, and we're going to quickly look at some of the performance that we can do. And Paul's also run into the next bug, what happens when we hang the server. When you hang the server, VMware Tools isn't able to run, and we can't get out of our console. So if you hit Control-Alt, we can get out, and we can now click on the vSphere client again. All these things that we found in the labs as a bazillion people have been running them. Oops. Alrighty. So we're going to go to the Performance tab for VM7. Thankfully, the rest of the environment still runs. We've just hung this VM. Hopefully it runs. We've all this. Okay, good. So now we're going to go to the Performance tab. We're going to go to the Advanced features again. We're going to go and look down into the memory. We're going to do real time. And we're just going to look at compressed, which is right here, which is the compression cache. It's not going to say anything right now because we're not using it. And we're going to look at swapped. Okay, and we've got to scroll down to say okay. All right, and so here we're going to see that, again, no history except if we scrolled over to the far right. But down in the legend, you'll see that we have started to swap out 200 plus megabytes worth of memory. All right, so we have assigned that limit. What is above that limit has to be swapped out to disk, and the performance has dropped. Let's see if he's upset yet. He is still hung. Perfectly fine. It still shows the thing. It hangs. All right, it's bad. Okay. Go to the resource allocation for VM7. So we saw through the Performance tab in the Advanced button the raw numbers. But another nice thing is just on the Resource Allocation tab, you get this really nice little bar chart, colored bar chart here that shows what the allocation of memory is. So at the bottom, you see that we had configured 800. We put the limit at 512. And now what's going on is as it's swapping out to disk, the resource, by the way, the Resource Allocation tab here does not have a refresh button on it, so it's a little bit out of sync with what the Performance Advanced tab is. That was doing real-time metrics every 20 seconds. It got updated. So before we had saw it was 200 something. Right now we're only seeing that it's 179. It hasn't updated quite yet. But the red in the bar is the swapped, and there we just updated good. And it's updated to 287, and private is 512. And because I'm really interested to see if he... there! Finally, if you're waiting in the lab, you finally got the payoff. It finally showed red. Okay. Alrighty, so we're going to power down that VM, and Paul's going to do this in the background because it takes a little bit of time. We're going to power down the VM. Actually, we'll watch it. Yeah, so shut off the VM. Okay? And now we're going to enable memory compression. Now, memory compression is enabled in the EXX host level, so Paul's going to select the EXX host. He's going to go to configuration, and we did it very quickly, but there's an advanced configuration or advanced settings tab underneath the software box. There's two boxes on the configuration screen. There's a hardware box and a software box. Both of them have advanced settings. It has to be the software box down at the bottom. And you'll see that there's the mem setting here. And if you scroll 90% of the way down, you can see that there's a field called memzip enabled. And right now it's 0. Again, by default it's on. It would be 1, but we have to, for the purpose of this little demo, we had disabled it. So he's going to set it to 1 and say OK. Alrighty. Now we're going to go and unset the memory limit on VM7, and we're going to do all this in the background. But we're going to unset the memory limit just so that the VM can boot up pretty easily without having to do any swapping or anything. We'll turn him back on, power him up, open the console, and we'll see that the little happy guy is happy again, and then we'll go back through it. While we're in the slides, though, I just wanted to go through a couple things. We've seen this before. We've got the nice swapping and swapping here. Now, a couple of numbers to remember for a little bit later on. We have this 800 megabyte assigned to the VM. It thinks it can use that much. We've set a limit of 512. That's how much physical memory it's allowed to use at the EXX host level. All right, what do we see at the bar chart? We saw that it swapped that out to disk. And we saw that private, this is what's actually physically in memory. It's not compressed. It's not doing anything. It's physically in memory, one-for-one mapping to some degree. And it's 512. It's exactly what our limit is. All right? Now, with memory compression has to use, and we saw these advanced things, memory compression has to use up some memory. So if we compress 300-something megabytes worth of that original 800 megs that was assigned to the VM, if we compress 300 of that, it still compresses down to something. It doesn't just disappear like when we swap out to disk. When we swap out to disk, we free up, for every page we swap out to disk, we free up a page of memory in the server. For compression, we have to compress it. So we can take 2 pages and free up 2 to 1. Or we can do 4 pages and swap it down, or compress it down into 1 page in memory and free up 3. So we still have to use some amount of memory. And when we see that in the exam a little bit later on, we'll see that. All right, I just wanted to quickly go over here. We're going to actually switch back to the view. All right, so we've powered him on. We've unset the memory limit. And so he's pretty much back where he was before, the 570-something range. It looks like, oh, he's just got into the happy range for a second there. OK. All right, so we're going to go ahead and reset the limit one more time. All right, so we have memory compression on this time, and we're going to reset the limit. OK. Now, we'll notice that the performance doesn't drop really, really quickly. And that's because we have free memory, so the VM is allowed to keep on going for a while. If we really, truly had memory and EXX had to free up memory instantaneously, it would either have to pause the VM, it would sort of slow down a lot while it swaps things out to disk or does ballooning or something else. But we do have a little bit of free memory still, so it's able to take its time a little bit. And right now, it's compressing pages and doing things like that, and it's going to take a little bit of time to stabilize, and because resource allocation takes a little bit of time to update and we don't have the refresh button, it's going to do its thing in the background. All right? Okay, so hopefully you know about our other memory overcommitment technologies, transparent page sharing. This is the deduping technology we have. It works on small pages only, and by default nowadays, your EXX pages, at least at the EXX hypervisor layer, are large pages. And transparent page sharing is not going to work on the large pages because the large pages are so large, the odds that we have a large page that maps completely identically to another page, that they're exact copies of each other, are statistically kind of small. With small pages, though, the odds are that we will find another one if it's a common operating system, common libraries, things like that. So transparent page sharing, it'll find however many pages that it can find that are exact copies. It'll just say that there is one page in memory, it'll just use one page, and it'll just send links to the rest of them. And as you change one, it does the copy on write, it makes a copy of it, and it assigns that as it changes. All right, ballooning. The ballooning is our in-guest technology. This is what we had before. We had transparent page sharing, ballooning, and EXX swapping. That's the only things we had. So if transparent page sharing didn't work, the only thing we had left was to swap out to disk. And in general, swapping out to disk at the guest level provided better performance because the guest knew exactly what that memory was being used for. It knew how frequently the memory was being accessed. And so it had much better knowledge of how the memory was being used. And it could say, these pages, they haven't been touched in quite a while. They're safe to be swapped out to disk. That was great. EXX, the hypervisor, the lower layer, it doesn't keep complete tabs on every single physical page of memory that a VM is using. It's not keeping that up to date as well as the guest operating system is. We do have a measurement inside vCenter that says, active memory and things like that. That's a statistically sampled measurement. It'll go out there and sample 100-something pages and keep track of those 100 pages of your memory and say, 10 out of those 100 pages are currently being used. Oh, you must have 10% active memory. It's not keeping track of every single page. And so when we start having to find pages to swap out, we do it randomly. We just randomly pick some, we swap them out to disk. If they happen to come back in, we randomly pick some more. And over time, hopefully we get the least recently used ones out to disk, but it takes a while to stabilize that way. All right. What we now have is memory compression, and we'll go into memory compression. It's yet another layer. It's designed to work with the balloon driver, in 4.1, that feedback isn't completely there, but they are designed to work together. And here's a very, very basic example we have with the caveats that transparent page sharing is not on here, large pages, and other things. But anyway, a one-to-one mapping is our simple view of the world. One page of virtual memory that the VM gets to see maps to one page in the hypervisor. When we have the memory overcommitment situation and memory pressure, we start looking for pages that are good candidates for compression, have a lot of white space in them, or a nice repeatable pattern. And we run a compression algorithm on it, very similar to a gzip or a regular zip. And we run the same algorithm across all the pages that we think are good candidates. And if we can compress them down to 25% of their original value, absolutely great. We put them we find 4 of those that we can compress down to 25%, and we put them on a single page. If we would only compress this down to 50%, then we'll put 2 of those, 2 50%ers on one page. It only does the 2, right? We want it to only have to keep track of a couple of different sizes. So it's not just, it compresses and that's how much it uses in physical memory. If it can't compress it down by 50% or more, it gives up. It goes to a different page, all right? And the whole concept here is that swapping out to disk is a very slow procedure. And doing things in memory, so when we do memory compression, it's all in memory and never goes out to disk, we can do things significantly faster. So a decompression, taking that compressed page and uncompressing it so we can give it back to the VM and allow it to use it, takes on the order of 20 microseconds. Versus swapping out to disk and bringing it back in. Just bringing it back in could take 2 milliseconds. There's disk latencies of milliseconds, on the order of milliseconds. So an order of magnitude difference from in-memory, memory compression, and swapping from disk. All right, and one last thing. I see on the screen here that it has finally done its thing. But one last thing. We've got internal test that we did, and we've published this on the VMware.com website, but our performance team did a quick little test with SwingBench, the SwingBench benchmark, which has Java. It's a pretty memory-intensive benchmark. And they created 16 VMs on a single server. They used just swapping and just memory compression, and they plotted the performance as they reduced the amount of memory that the VMs were allowed to use. And you'll see that when they had all the memory they have, they normalized that it had good performance. We dropped the memory down a little bit. The performance for both of them didn't drop too much. As we drop the amount of memory that the VMs are allowed to use, swapping, which is the red line, really drops in performance compared to the blue line, which is the memory compression. And you can see that memory compression provides you some nice little gains compared to swapping. And we can see 15 to 25% improvement over swapping with memory compression with some memory-intensive workloads. All right, we're going to swap back to the lab. And if you could scroll over, hopefully he's not upset. I haven't seen that portion of him. Alrighty, well, there he goes. Okay, all right. He's a little finicky, but you'll see that he's actually a lot happier. Before he was red, now he's in the 100, 200s range. Now, in the beginning, when he had all the memory he wanted, he was right up there at the 600 range. He was just at the top of the yellow-green range. But now he is having a little bit of a performance issue, but he's a lot happier than he was before in the red zone. Go back up. Alrighty, let's go over a little bit, slide over a little bit because he's red right now. Hide that. Alrighty, so what's happening here? We've compressed a certain amount of memory. So we've compressed 300 megabytes, and it's taking up a certain amount of space. And I reminded you to look at the private Before it was 512, now it's 432. So the non-compressed memory that your VM is allowed to have in this little example is only 432. The rest is being used by the compression cache, by the memory compression cache is what we call it. All right, so we've compressed 300. It's still using that portion of it in memory. And then we still had to swap out a little bit. And I left that in there and because this is what you would see by default. Memory compression will only go so far. By default, there's a certain percentage of your assigned memory that you've assigned to the VM, and in this case, it was 800 megs that we assigned to the VM. A certain percentage, and in this case, it comes out to be 300 megabytes, is all that memory compression will attempt to do. After it hits that number, it says, we've already started to compress a lot of your memory down, and let's do something else. So it's going to start swapping things out to disk, because again, when you swap something out to disk, for every one page you have to swap out to disk, you free up one page, whereas memory compression doesn't free up exactly that same ratio. So anyway, we do have a little bit of swapping, and actually that swapping is what is probably causing the performance guy to be a little bit more unhappy than he normally is. But anyway, we're going to switch back. I think that's pretty much the end of the memory compression one. And we're going to switch back here to the slides. This is what we were seeing, and again, just note that he is using up a little bit of your actual private data in order to keep that compression cache someplace. And we'll just wrap up the best practices here. A little bit of a memory overcommitment is probably just fine. We have a lot of customers that are afraid of it, but it's probably fine. If you are using memory overcommitment, make sure you're using transparent page sharing. It's on by default. It's another thing that you probably never would want to turn off. Use your balloon driver, so install VMware tools. But before, and I'm going to make the recommendation here, and this recommendation is only if you absolutely want to optimize your performance, go in and customize your balloon driver and try to tweak it such that it won't start swapping things out to at the guest level to disk before memory compression can do its thing. Now, ideally, and in later releases, hopefully this feedback will be improved some more, the idea here is that we want to have the two technologies working together with each other. So the idea would be we start ballooning. Maybe there's free pages in the guest operating system that are just not being touched. We inflate as much as we can, swap those pages out to disk. That's not going to be a performance problem for us, right? They're not being touched that often. The guest operating system knows that. So we start doing that. Once the balloon driver starts inflating too much and we start swapping things out to disks and things have to come in and out of disk, we want to be able to detect that, back off so that we're not swapping out at the guest level, and allow memory compression to start doing its thing. And once memory compression says, all right, I've completely done my thing, we have to then allow the HX server to do its random swapping out to disk. So there's supposed to be this feedback, but in the meanwhile, if you really wanted to get your best performance, you could set a maximum limit on how much your balloon driver will swap out at the guest level. All right, and then use memory compression. Again, it's on by default, no reason really to turn it off. If you do have a memory-intensive application, Java does come to mind. They're very memory-intensive as it has to sweep through its entire heap every once in a while to do the garbage collection. Do assign memory reservations. So if you're going to have memory overcommitment, make sure you assign the memory reservations to the VMs and workloads that absolutely need memory. Okay? And then in our little demo here, we looked at the swapped rate and compressed rate. And we did it for simplistic reasons, right? It was easier to see how much we swapped out to disk. The swapped rate is probably not the one you want to look at for performance measurements, because swapped is what is currently been done, right? But that swapped pages could be something that you swapped out there a week ago, right? And it just has never been pulled back in. It'll show up as swapped because it's out there in the swap space, but it's not really actively being pulled in and actively causing a performance problem. It's been out there for a long time and no application has requested it back again. Perfectly fine. The better measurement to look at is swapped in rate. How often are we going to the storage, pulling it in, because that is going to be a performance problem. Every time we're pulling it in for a reason. We're pulling it in because an application wants it, and that is going to cause a performance problem if we have to do that. So the swapped in rate is better. We throw in a little guidance here of 1 megabyte of your swapped rate. 1 megabyte is probably a little too high. Depending on what your workloads are, if they're memory intensive, you might, or sensitive to memory performance, 1 megabyte worth of swapping might cause you a problem. Even way less than 1 megabyte might cause you a problem. But we throw it out there as a guideline, as just a sort of a rough guidance. The last thing I wanted to mention is NUMA. It's becoming much, much more popular. Almost all the servers these days are pretty much NUMA-based. If you are going to be creating larger VMs, and that is both in terms of CPU larger or memory larger, try to make sure that they fit on a single NUMA node in your physical server. So each physical server has different NUMA characteristics, but if you do have a NUMA node in your particular physical server and it hypothetically has 2 CPUs in the NUMA node attached to 4 gigs of memory in one NUMA node, try to keep your VM within that range. If you don't have to, don't give it that third. Don't make a 3-way VM just because you want to make it slightly bigger. If it can fit in 2, fit it in 2. If it goes to 3, the EXX scheduler has a little bit more harder of a time trying to figure out what to do with that, because it has to put that third CPU someplace, and it'll be on the other node, and you'll have to have remote access to the memory from that node. If you keep it within a single node, the EXX scheduler is phenomenally smart. And it will start running your workload, and it'll try to keep you all within that same NUMA node. If it starts seeing that, oh, you know what, the CPU is getting contended in this NUMA node, the grass looks to be a little greener over there, it'll make a calculation, and it'll say, you know, should I try to run over there because I have free CPUs over there and just take the penalty for accessing memory remotely? And if it figures out, oh, that probably is a good thing, it'll move it. It'll temporarily put your CPU over there and access your memory remotely. If it starts running over here and says, you know what, the grass really is way greener over here, those CPUs are still heavily contended, it's going to start migrating whatever memory you have on that node over to the other guy so that you can start getting the benefits of having everything on the same NUMA node again. So if you can keep it within a NUMA node, good things will occur at the EXX level, all transparently to you. All right, we're going to have Paul take over from here and go into the CPU talk.
Right, so let's talk about that least important thing, CPUs. We don't need those, do we? In the lab, I'm greedy, so I get 2 ESX hosts. I just stole one from one of Joey's labs. We've got VM10, which is our main load. He's the one that's got the smiley face in there, and he's looking decidedly unhappy at the moment. And then we've got VMs 3, 4, 5, and 6. They're going to generate some contention. They're going to actually be CPU hogs, so they're going to take away the CPU that he hasn't already got. So let's dive into this. What I wanted to do first was just to quickly recap on how we virtualize CPUs, or why we virtualize them. So traditional physical hardware has an operating system running in what we call ring 0, which is a privileged mode. It can run commands directly onto the CPU, onto the hardware. Then along came VMware, and they said, actually, what we're going to do is we're going to take over ring 0. We're going to push the guest OS back to another ring. And in order to do that, we had to come up with some way of making sure that we could still run those privileged instructions. So we came up with binary translation. So we run a cache and we translate those commands. And when the CPU has to go off and do some of that work to do that translation, that's called a VM exit latency. And it goes off and does that. The hardware vendors thought this might be a good idea to get on this bandwagon. So they decided that they would design processors that would start to use the technology. And they just came up with this root privilege mode level, which allows our VMM, the hypervisor, to run inside a privilege mode of its own, allowing the guest to run in another, it's still running ring 0. So it's improved things. Originally, it didn't improve things much, but now it's getting much better. And we'll look as we go through into exactly what that means. So let's have a look at Mr. Smiley. So you can see Mr. Smiley up there. He's okay. He's not very happy, but he's not upset. Occasionally, he will dip. But if you look at VM10, he's actually got an error. Does anybody want to guess what that error might be? Let's go and have a look. Oh, what a surprise. It's CPU. So he's got a CPU problem. So the first thing we can try is we can give him more CPU. So we're going to give him a second CPU. Just a quick show of hands. Who thinks giving him a second CPU is going to fix the problem? Oh my goodness. That's the first time that's happened. So we're going to give him the second CPU. We had to power him off, unfortunately. It's a Windows 2003 machine, so we haven't got hot swap enabled. So while we're waiting for that to go through, let's have a quick look at what binary translation actually means to us. So in the good old days, binary translation, if we had 32-bit operating systems, we said that we'd use binary translation. If we had 64-bit operating systems, we suggested we use the hardware assist. But over time, as particularly Intel have improved their hardware virtualization, we managed to get these exit latencies down and down and down. So the penalty for using hardware virtualization has almost gone away. So now, basically, we use hardware virtualization. And I'm hoping it'll come back. So we'll go back and watch Mr. Smiley quickly, because he's nearly there. The machine's starting up. I'm sure you spent more than enough time in your careers watching Windows machines boot. And status bars is another of my favorites. So he's nearly there. So we're going to do something that we can't do in production. What we're going to do is we're going to live, as in front of you, convert this smiley face application into a dual-threaded application. So you're going to watch me code for a little while. Or maybe not. So as we can see, actually it's made absolutely no difference whatsoever. So Joey's just going to type the code in for me. It's actually a double click. And wouldn't it be great if you could do that in production? Because what I've just done is convert this into a dual-threaded application. And now, as you can see, it's actually not just doubled the throughput, it's significantly improved the throughput. So giving the application, the VM, another CPU with a single core, with a dual core but a single-threaded application makes no difference at all because it can only run on one thread. Giving it a second core to run on when we make it dual-threaded makes a huge difference. So topically, the next slide actually looks at some research that we've done, some experiments that we've done with multiple cores. So what we've got is you can see that the bars represent the number of cores, and then we've got the load at the top there. And as you can see, when we're using, when we've got headroom, when the physical host has got headroom, we don't have a major problem increasing the number of cores. The penalty is quite low. It's only when we get to, the saturation figure of around 80% saturation that we get a problem with multiple cores. So multiple cores don't cost us as much as they used to. Again, just to reiterate what Joey said about NUMA, if you've got a NUMA node, when you're designing and configuring your VMs, you really want to try and keep them within the context of a NUMA node and get away from this poor locality of memory. If you can do that, you will see a performance improvement. So what we're really concentrating on in this lab is looking at CPU saturation. So our little smiley face had reached CPU saturation on a single core. We gave him a dual core, made him dual-threaded, and we got around that situation. How do we tell if it's saturated? Well, if it's greater than 75% on average, if it's peaking above 75%, or we're hitting peak usage of 90%, then we really need to look at something else. So we go off and we look at this ready time. And if ready time is greater than 2 seconds, in fact, but 2,000 milliseconds, or 10% for any vCPU, then it looks like we've got CPU saturation and we need to do something about it. That can also exist inside the guest. So if we're same figure range, average use is greater than 75% or peaking above 90, then we've got CPU saturation. The great thing about virtual machines, of course, is we can do exactly what we just did, and we can actually give it a new CPU. A little more difficult in hardware, and a little more costly in hardware. So let's go back to the lab, and what we're going to do is we're going to make him unhappy again by turning on these virtual machines. And actually, the effect is pretty quick. As soon as we power them on, he gets unhappy. There we go. So, did somebody just turn them back on again?
Well, they were just...
Oh, okay. Somebody obviously gave me some more resource. So he's unhappy. So it looks like we've got some sort of CPU saturation problem. So one of the fixes we can do is we can set up a resource pool. We can check that first. So we can go into the graphs. What we're looking for is, really we're looking at ready time. and we're looking at usage. The VM on the VM. Mm-hmm. So just cancel.
Oh, good. Thank you.
Oh, I could have used that scroll bar. So we just want to see what's going on here. If we hover over this, we'll see that we've got ready time of, 382 milliseconds. But over here, it's gone way sky high. So we are indicating some sort of CPU saturation with that VM. So one of the things we can do to fix this is to set up a resource pool. So we can set up a resource pool, and then we would take our low priority VMs, we'll drop those into the resource pool and fix it that way. So the first thing we're going to do is turn on DRS. Then we're going to go and create a resource pool. As you can see, we're very authentic in our naming. We're going to give it a silly limit just to make sure that it does actually a really silly limit this time, just to make sure this bit works. We're going to give it a really silly limit, and then we're going to start to drag and drop our virtual machines into that resource pool. So we're restricting the amount of CPU that they can use quite substantially. Of course, this won't happen instantly. It's going to take a little while for this to balance out, but it will balance out. We did say at the beginning of the presentation, your mileage may vary, so there are some penalties to being the third most popular lab. Maybe. There we go. Yay! Excellent. So you can see that kind of worked. What we're going to probably see in a minute is that actually we're going to get some fluctuations in his performance, which we might want to do something about. So we enable DRS. So the way that we can get rid of those fluctuations in performance is by using DRS. So we'll go to the DRS tab for this cluster, and we'll run DRS manually. And hopefully, I'll give you one guess what the recommendation is going to be, and we just apply the recommendation. Okay, we'll come back to that in a minute, and we'll prove it's worked. So another way that we can measure our environment, who's used ESX Top before? Okay, it's one of my favorite tools, mainly because I come from a Unix background and it looks like Unix. We've got ESX Top. We can look at the world ID, so that's a process number. We can look at the group or parent ID, so we group them together. Each VM will have a number of worlds. By default, it'll have 3 worlds. One world for the keyboard, one world for the VMM, and one world for each CPU. That tells us that we can see how many worlds we've got. More interestingly, we can see the usage, and we can also see the ready time, so we can see it at a glance. The great thing about ESX Top is we can actually drill down then into look at individual virtual machines, so that makes it a bit more useful. And of course, that compares to the graphs within vCenter itself. Now, we've shown a high usage or a high ready time indicator here. That's not always an indicator of a problem. There can also be problems when we're seeing low usage, when we're expecting higher usage. So what can cause low usage is an external problem. So if we're swapping, for instance, we can have a problem whereby we're waiting for the swap memory to come back in. And we can tell that in ESX Top using that percentage swapped out, swap wait, indicator. That shows us that it's spending time waiting for memory to come back in. The other problem is co-scheduling. So where we've got machines that have got multiple CPUs inside them, they're waiting for all those CPUs to be scheduled at the same time. And again, we can see this within ESX top using the co-stop indicator. And, of course, we may have set the limits. Those other machines that we've set up in here are all waiting for CPU because we've set limits on them. And we can see that. If we set a limit, we can see that it's actually stopped by a limit from an ESX top indicator, the percentage limited. Who's used it? Sorry, go on. We're not going to go into that now, but we'll talk about it afterwards if you want to come and talk to us. Okay, so who's used ESX plot? Who's come across ESX plot? Okay, a couple of people. That's following the pattern. It's a great little tool. You can download it. It's free. It runs on Windows, Linux, and Mac OS. What it allows us to do is take the data that ESX top produces and take it offline and examine it offline. So the way that we do that is we capture the data from our ESX environment. We capture it in batch mode using ESX top or RSX top in batch mode. Then we import that data into ESX plot, and then we can examine that at our leisure. And, of course, it takes it out of the environment, so we can examine it without affecting the environment in any way. You do have to make sure that when you're running ESX top, you've selected all the values that you want to capture. So it's very easy to import. You just take the file, it's a CSV file, you import it as a data set, and then you can go off and examine it. So we've got three parts to this screen. One is the metric that you're trying to measure. Whenever you select a metric, it gives you a summary of the metric in the summary window. And then, of course, we get nice, pretty graphs and things that we can show to justify us spending more money on hardware or whatever we need to do, or just to justify our existence. Who's got the VMA in their environment? Oh, that's a low number. Usually that's a lot more people. So the VMA is a great thing to have in your environment. It's an appliance, so you just import it into your environment. It is a great place to run RESX top, but it's also a great place to run things like the SDK for your ESXi hosts. Also to run, you can run it as a system log catcher and various other bits and pieces that it can do. So other performance enhancements that we've made within 4.1. We've vastly improved vMotion. Who saw the keynote on Tuesday? So that was indicated in there. We've increased or decreased the stun time so that the machines move very much quicker, and therefore you can do more of them. You can do up to 8 now. Joey alluded to this, the VAAI, which is the ability for ESX to offload some of the work that it would do with storage to appropriately equipped storage arrays. If you're using NFS now, we can actually see NFS statistics inside ESX, which is particularly good news, which gives us a better indicator of what's going on there. And also what we've done is we've improved NIC teaming, so now we can do load balancing across a NIC team, which is good news too. Just a quick recap of some best practice. Storage latencies, if it's greater than 30 milliseconds at the device and greater than 2 milliseconds in the kernel, that's a bad thing. We need to look at that. We've probably got a problem. If we're checking for CPU, we need to check utilization, the ready time. Utilization, obviously, we want fairly high, but at the same time, we want ready time and co-stop to be low. We also want to check to make sure the balloon driver is not being overused, so we want that if it's non-zero. And also, of course, swapping is going to cause problems, as we've seen dramatically today. And some of the configuration mistakes. So a lot of modern hardware has the ability to throttle down the CPU if it can, and we want to turn that off. And obviously, you want to tune your applications. If you're really interested in more stuff around this performance and troubleshooting, then there are some various sessions that you can attend. Have a look at those and go visit those. And of course, if you haven't done the lab yet, go downstairs. Little tip, the labs are really quiet later on in the afternoon. They close at 6 today, but between 4 and 6, they'll probably be quite quiet. Please don't forget to fill out your surveys, and thank you very much for your time.